Hi, this is Camille Fairborn from Michigan State University, and I'd like to welcome you to today's Cause Teaching and Learning webinar. We're pleased to have as our presenter today Dr. Dennis Sun, who is an assistant professor in the statistics department at Cal Poly San Luis Obispo and a data scientist at Google in Mountain View. For today's webinar, he will give a presentation entitled, "What Should We Teach in Data Science Courses?" The way the webinars work is that all listeners are muted during the webinar. You can ask questions at any time by typing them into the questions box, and we'll be sure to ask those questions towards the end and give the presenter a chance to respond. You can also use the chat box if you're having any technical questions or issues. At this point, I'll turn things over to Dr. Sun. Dennis, go ahead.
All right, thank you so much, Camille. So as Camille said, my talk today is about what should we teach in a data science course. And I'm going to draw on some of my experience teaching a data science course at my school, Cal Poly, and also on my experience working as a data scientist at Google. So I think most of us are familiar with the idea of data science. So data science is sort of a new discipline, it's a buzzword. And the basic idea is that it's a discipline focused on how do we extract insight from data. And so there's also a lot of hype around the job title of data scientist. It was ranked Glassdoor's #1 job in America in 2016 and 2017. So clearly it's a job in demand in the industry. And so one question that I think many of us have is, what exactly does a data scientist do? And how can we as academics, as educators, prepare students for these new jobs? And there's a lot of disagreement about what data science is exactly. And there are lots of papers you can read about sort of the different definitions of data science. But nevertheless, even though we're not exactly sure what data science is, we have majors and master's programs across the country springing up. So even though we haven't exactly settled on what data science is, that hasn't stopped people from offering data science courses and data science programs. So what I'm going to offer is sort of some working definition of data science. I don't really want to sort out the debate over what data science is, and I want to focus instead on our points of agreement, what we agree on. And generally, I think most people would agree that data science is a discipline that involves skills from both statistics and computer science. Now, compared to traditional statistics courses, there's this idea that there's more focus on data manipulation, data visualization, and computing than in a traditional course. And there's comparably, I would say, less of a focus on formal procedures, like, for example, checking that all the assumptions are satisfied before doing ANOVA, for example. But I would argue that it's not because ANOVA or inference is not important. I would say, if anything, inference is more important than ever in data science. Understanding variability, understanding the difference between signal and the noise, those are very, very important issues to the practicing data scientist. Now, compared to a traditional computer science course, I would say there's more of a focus on how to frame questions. And in my experience taking computer science courses and even teaching computer science students, a lot of computer science students, what they want is they want a spec. So they're very used to this idea of you give them a specification of exactly what you want their program or their code to do, and then what they do is they implement it. And data science doesn't quite work like that. A lot of data science questions are vague. They're real-world questions that don't necessarily have one answer. And I found in my experience that a lot of computer science students are kind of uncomfortable with that ambiguity. And even if you look at CS courses that we would consider data-centric, like a course on, say, databases, where the students are writing queries, database queries, the focus of those courses is on how do you write queries to reproduce some expected output that the instructor wants. For example, if you had a table of people and their friends, if you had that stored in a database, a question might be like, how many of Bob's friends are also Alice's friends? Right? That might be a question, and then the students write a query to answer that question. A more data science-y question might be something like, are friends of people with a lot of friends, do they tend to have more friends? And that's a much vaguer question, and that's a question that you probably couldn't even answer with just one query. And I would say what we want is we want to try to get students to think about how to answer those questions rather than just trying to write a query to answer a very concrete, specific question where you know what the answer will be. So my conclusion is data science is not redundant. It's not just statistics, or at least traditionally what we've called statistics, and it's not just computer science, what we've traditionally called computer science. So there really is a need for new courses to prepare students for the data problems of this century. Now, I've said that the focus of this talk is going to be, what should we teach in a data science course? Now, I want to emphasize that word course because this is different from asking, what should we teach in a data science program, which I think is also a question that's interesting to a lot of us. Now, a data science program should ultimately prepare students and equip them with all the skills that a practicing data scientist would need. And that includes everything from statistical modeling, like linear regression, machine learning. They need some training in databases and writing SQL queries. They may even need some training in distributed computing, and so forth. So there's actually a lot of skills. But I would argue that a lot of these skills are actually covered by existing courses on our campuses. So you can take a course on regression modeling. You can take a course on machine learning. You can take courses on databases. So what I want to focus on today is sort of what ideas are not covered by our existing courses. So you might take a course on machine learning. You might take a course, introductory course in statistics and regression, but there are some topics that kind of fall through the cracks that a data scientist needs to know, but are sort of not covered by any of the courses that you would take in a statistics or a CS department. And those are, I would argue, are the ideas that should go into newly designed courses called data science. And so that's what I want to focus on today. What are those ideas and what should we put in these courses? So just a little bit of background about myself. I started teaching an intro to data science course at Cal Poly since I joined. That was about 2 years ago. And each time I've taught it, it's actually been quite different because when I first started out, I wasn't exactly sure what should be covered in a data science course. But I think I'm gradually sort of settling on the following 4 big ideas. And my talk will focus on these sort of 4 big ideas, which I would argue are ideas that our existing courses don't quite completely cover. So the first big idea is manipulating data. How do we think about and work specifically with tabular data? Because a lot of the methods that we look at in statistics courses and a lot of the libraries that we might use, they sort of assume that our data is in this tabular format, and I'll explain what that is in a second. The second big idea is, how do we frame questions? I sort of mentioned this idea that data scientists often have to translate these vague real-world problems into actionable data analyses. So, and that's a very, very important skill that I think students actually struggle with. If you give them a very concrete thing to do, you say, tell me what this number is, they can often do that. But they often struggle to translate something that's vague into something that they can actually answer with data. The third big idea is, how do we communicate these results? So communication can happen in the form of graphics producing visualizations. It can happen in the form of tables. It can happen in the form of reports. So what are some principles for creating compelling, insightful, and accurate graphics, tables, and reports? And the last big idea I have here is thinking about the different ways that data can be represented. And in particular, we're very used to, and in statistics classes, we often focus exclusively on tabular data formats. So we give students a CSV file, and then they go and fit linear regression on that data set. But oftentimes, modern data comes in non-tabular data formats. For example, you might have data that's hierarchical, and you might have data that's just raw text, and you have to do something with that. So one important thing to train students in is, how do you handle and work with these new data formats and actually get some insight from those data formats. And as I said, I think those data formats are increasingly common in modern applications. So let me go through these 4 ideas one by one. So what do I mean by manipulating data? Manipulating tabular data in particular. So here's some data that I actually have my students analyze. This is data from the Boston Marathon in 2010. And so what I've shown here, so for those of you who are not familiar, I teach my course in a programming language called Python, which is very similar to R. It's a more general purpose language than R is. So people use it for everything from making websites to programming sort of production applications in Python. So And what I've shown here is something called the Jupyter Notebook, which is a very common way for data scientists and people who do scientific computing to interact with Python. And so what you see here is one cell of a Jupyter Notebook. So you write some code in a cell, and then you can execute that cell, and it will show you the output. So here, what I've asked for is just the head, the first couple of rows of this data frame called Marathon. And it gives me sort of the first couple of rows of this data frame. Now, if you look at this data frame, this is tabular data where rows represent observations. So I've shown that in red here. So one of the big ideas that we need to get across to students is thinking about what the observational unit is. And in this case, each row represents a runner. Now, as we process this data frame, the observational unit is going to change. The rows are going to mean something different. The second thing we need to get across in tabular data is that the columns represent variables. And so you can see each column represents a variable. And we want to get across sort of the different types of variables. So of course, there's the usual, there are categorical variables in the data set and quantitative variables. Some are continuous, some are discrete. And those are all things that we teach in our intro stats classes. I do want to draw attention to another type of variable that we often don't talk about in our intro stats classes, and that's sort of this other type. If you think about this name column here, it looks like a categorical variable. It actually isn't a categorical variable because the names don't repeat. So you don't analyze this column in the way that you might analyze a categorical variable where you count up, for example, how many people came from each country. This name variable sort of is unique. It's almost like a key in a table. So I think it's also important to emphasize to students that not all variables that they'll see in a real data frame fall sort of neatly into this categorical quantitative dichotomy. Now, one thing that we need to do is we need to actually give students experience with working with this data and cleaning it. So you might notice, you might if you look closely at the numbers here, you might have noticed that there are some runners with marathon times that were under 2 hours. And if you know, the world record for the marathon is over 2 hours, is just over 2 hours. And so how is this possible? So giving students experience with this sort of authentic data, I think, is very important. And so one thing we might do is we might just filter to just the runners. It turns out that these people, you see, if you look at their bib, they have a W in front, and that's because they were wheelchair competitors. So there's actually a division in the Boston Marathon for wheelchair competitors, and it turns out you can go faster in a wheelchair. So if we want to just restrict to just runners, and so we can have a fair basis of comparison, well, we might have the students learn how to filter this data. So one thing you could, so I don't even tell the students this. I give them the data set and just tell them to answer some questions for me, and they have to figure out that these are actually anomalous observations. They have to figure out that they need to clean this data set, and they have to figure out how they're going to clean this data set. And one thing that students often realize is that if you look at the division tells you sort of how many people are in the division and what rank this person came in that division. So if we look at the wheelchair people, their division ends in /22, and then the male and females are in separate divisions. So if you just restrict to the divisions that end with /4660 or /4996, then you'll get a data frame of just the runners in this data set. And so this code is Python, but it should be pretty comprehensible to those of you who use R. It's very similar to how you might subset a data frame in R as well. So one thing that we need to get across when working with tabular data is how do you actually go about cleaning the data? Now, another thing, and this is something that I think we don't really expose students enough to in our data science classes, is something called the split, apply, combine paradigm. So I might ask the question, how would you figure out who was the fastest male and female from each country? And the way students might do this is they might write sort of a nested for loop. They might figure out for all the countries in my data set, for all the unique genders in my data set, I might do something. I might try to subset that data and then figure out who is the fastest person. But it turns out that this is actually a very common pattern in data analysis. As data scientists, you're basically doing these kinds of analyses where you split along some variables, then apply some analysis, in this case, find the fastest person, and then you combine all the results at the end. So this pattern is so common that tools have been developed to carry it out. And so in Python, the way you would write a code is you would say runners.group by country and gender, and then we want the minimum official time for each person. So this gives us a data frame where each row represents a country gender pair, and then the value is the fastest time for males from Argentina or females from Austria, or Australia, I guess, females from Australia, males from Austria, and so forth. So this code is probably familiar to those of you who are familiar with the tidyverse, who use, for example, dplyr. It's very similar, same idea. Take a data frame, you group along some variables, and then you apply some analysis within each group. And so this is a strategy that I think that's fundamental to working with real data that we ought to teach more in our data science classes. A third idea in sort of working with tabular data is the idea of the different ways you can actually represent tabular data. So there are two main formats. One is called tidy data, and I borrowed this terminology from Hadley Wickham. And in tidy data, you sort of have one row per observation. So the data that we had earlier, where we had one row per country and gender combination, and then we had the time, the fastest time for that country and gender combination. This is an example of tidy data. And this kind of data format is often convenient when you're running regressions, because now you have your categorical variables and you can easily regress on them. But at the same time, this kind of format doesn't make it easy for us to compare, say, male times across different countries or female times across different countries. So sometimes it's actually convenient to pivot this table so that you have one variable going down one axis, so country going down the rows, and then the other variable going across the columns. So here I have gender going across the columns. This makes it easy for us to compare all the female times and all the male times compared to the sort of tidy format. And this format, and this is borrowed from the some of the database literature, is often called the data cube, where each dimension represents a different variable. And so if you had more than two variables, you can think of this as sort of a hypercube. And so we want to expose students to both types of representations. I know that in the tidyverse, people tend to focus on the tidy representation, and it's true that it's very convenient for analysis, but sometimes it's actually just much more convenient to present your results in sort of this cube format. So again, thinking about these different types of representations, the different ways to get across, communicate the same information, I think is a very important skill. And then the last thing I want to bring up when working with tabular data that I think is really important to emphasize is thinking about relationships between columns, relationships between variables, and also relationships between rows. So that's relationships between observations. Now, I think all of us are very comfortable with the relationships between columns. We emphasize this a lot in our statistics classes. We know that if you have two categorical variables, you might want to use a contingency table. If you have two quantitative variables, you might use a scatter plot. And we teach students many different ways to look at relationships between two variables. One thing that I think we don't do enough of in our statistics classes is emphasizing relationships between observations. For example, how similar are these two runners? Right? Each row represents a runner. How similar are they? And this is actually really important, because if you think about lots of machine learning algorithms like clustering, hierarchical clustering, and k-nearest neighbors, they're all about measuring distances between observations. So also teaching students how to think about how similar two observations are, that's also, I think, a very important skill that's underrepresented in our statistics classes. So those are some of the things that I think that we might want to do when working with tabular data. Now I want to talk a little bit about teaching students how to frame questions, to turn vague real-world questions into actionable data analyses that they can actually do. So what I found is that students often know the methods, but they don't know when to apply those methods. And what they need help with is translating these real-world problems to questions that they can answer with data. So some examples of real-world questions that someone might have is, is the effect real or is it just noise? And that's why I said that I think in data science, inference is actually more important than ever. Understanding this idea of sampling variability, understanding the logic of hypothesis testing, those are very important real world questions because oftentimes you'll see a difference in the real world and you'll want to know, is that just noise or is that something I can actually believe in? And so I think that it's really important to teach students those ideas of statistics. And this is something they actually get from their statistics courses. Another important real world question, and again, that I think statisticians are well equipped to teach, is what is causing the effect? So we see an effect, but what variable is actually driving that effect? And this gets into issues of experimental design, observational studies, and causality. Another real world question that's very popular especially in business applications is, how do I identify similar subgroups in my data? So someone in the business world might call that market segmentation. As statisticians, we'll recognize that as a clustering pattern, a clustering problem. And so that's a pattern that we want students to recognize. And the last example that I have here is, how do I predict a variable of interest? And of course, when we get into sort of prediction problems, we're getting into machine learning, and in particular, supervised machine learning. So those are all sort of common general patterns of real-world problems that we can teach students to recognize, and we can give students tools to solve those real-world problems. So I want to focus on just one of them, which is what is causing the effect. So what should we teach students about causality in a data science course? Well, we can teach them about confounding, the problem of confounding in observational studies. We can teach them about randomized experiments and how that mitigates the problem of confounding, as well as strategies like blocking to reduce variance, to reduce variation. And those are all ideas that we actually do cover in our statistics classes, our intro stats classes. Something that we don't cover as much is, well, once you buy the story of sort of confounding, this idea that you might have confounding variables, well, why don't we match on the confounding variables to try to control for them? So if we have an observational study and we match cases based on possible confounding variables, then we might actually be able to do causal inference subject to some assumptions. And this is something that we don't really cover in our intro stats courses, possibly because it's actually not easy to do. It's not easy to do, and every problem sort of requires a custom solution, so it actually requires writing some code to do it. But I would argue that our data science students actually have the computational tools to actually explore the confounding effect in real data and to think about how we would actually go about adjusting for it using techniques like matching. So let me give an example. So this is not really a traditional sort of question of causality, but this is something where we see an effect and we want to know what is causing that effect. So one thing, if you look at that marathon data set and you group by country and you look at the average time by country, and you look at the times for Portugal and the US, you'll see that the Portuguese runners are on average 3 minutes faster than the American runners. And so we might be interested in what is driving this effect. And so my argument is that the students can actually write code to explore what's causing this effect. So let me just show you. Now, one thing a student might think is, why don't we look at the average by gender? So one thing you might do is, instead of just grouping by country, let's look at the average time by country and gender for Portugal and the US. And when you look at females in Portugal versus females in the US females are faster. And when you look at males in Portugal versus males in the US, males in the US are also faster. So people in Portugal are faster overall, but both females and males in the US are faster. And one thing to make the comparison a little bit easier to do is, right now, this is sort of the data in tidy format where we have one row per observation. We might pivot this table into sort of cube format, data cube format, where we have country going here and official time going across, gender going across. And this makes the comparison a little bit easier. And again, we can see that US males and US females are faster than Portuguese males and females correspondingly. So what is going on here? Well, we can look at the counts. Why don't we, instead of calculating the mean by country and gender, let's figure out how many males and females were in the US and in Portugal. Well, it turns out that most people who run the Boston Marathon are from the US, so there weren't many people in Portugal. There were only 6 people, 4 of whom were male and 2 of whom were female. So Portugal has more males than female. In fact, twice as many males than females. On the other hand, the US had more females than males. So it's the gender imbalance that was driving the effect. On average, males tend to be faster than females. Even though males were faster in the US and females were faster in the US, the runners in Portugal had more males and the runners in the US had more females. And so as a result, it looks like overall Portugal is faster than the US, but when we actually include gender into the analysis, people in the US the runners in the US are faster. And so, of course, this is just an example of Simpson's paradox, which many of us are familiar with and teach in our intro stats classes. But I think what's critical here is that the students were actually able to explore this effect for themselves using the computational tools that they have. And so that's why I think it's different about a data science course, is that we're actually thinking about blending the computation into the course, which allows the students just to do a lot more rather than sort of giving them the data in this sort of pre-processed format. We can actually have them explore these questions for themselves. And so I think that's a good case study that shows you sort of the kinds of explorations that a data scientist would do, and that they would do if they want to answer the question, what is causing a particular effect? So the third big idea I mentioned of a data science that we might want to get across in a data science course is, how do we actually communicate results? So I'm going to focus mostly on graphical communication here. I think most of us teach in our stats classes that the following bar graph is an example of a bad bar graph. And the reason, okay, so this is purporting to show the average time by age in the marathon data set, and we split by gender, so we have females and males. Now, why is this a bad bar graph? Well, because the bars don't start at 0, and so this bar graph is misleading. It sort of makes the differences look bigger than they actually are. So I think, I think most of my students know that this is a bad graph, and they would never turn in a graph like this to me. But I still get senior statistics majors making graphics like this all the time. So here you have the average official time by country, and they might make something like a line plot here. And here you have the average official time by age, and they've made a bar graph. So this one is correctly anchored at 0, but I would argue that this is still a bad graphic. So why are these bad graphics? Well, here we have country on the x-axis. There's no real ordering to country. And by making a line graph, by connecting them, we're sort of drawing attention to the relationships between these different countries. And so the connections between these lines is somewhat misleading. I would argue that a bar graph this is not an egregious plot, but I would argue that bar graph is not the best plot here, because this is just the opposite. Age is ordered, and we want to emphasize the continuities. Age is ordered, and we want to emphasize what are the trends in the average time by age, and the bar graph sort of breaks up that trend. Now, how can we teach students to make better graphics? So these are not, I would argue that neither of these graphics are wrong. They're not technically wrong, like the bar graph that doesn't start at 0. But I would argue that there are very subtle issues with these that reflect a lack of attention to the first impression that these graphics will make on an audience. And that's what I think we ultimately want to get across. So our data science courses should prepare students to write and present with their audience in mind. And if they're really thinking about what is the audience's first impression when they see a line graph like this, they might think, oh, well, they'll look at the connections between these different countries, and that won't make any sense. That's the kind of thinking we want students to automatically have. And so what I would argue in what we should teach about communication is thinking about what the audience's first impression will be, sustaining their interest through narrative and possibly even suspense, and also summarizing the take-home message at the end, just to recognize that the audience may not have caught everything and they may not know what the important points are. And when you summarize something at the end, that can help them know what to take home with them. And these are things that I think us as educators are very used to thinking about, because every time we design a lesson, we're thinking about what our students' first impression going to be, what are they going to take home with them. So we're really thinking about that all the time. And I think it's sometimes we forget that this doesn't necessarily come naturally to all students. So I think it's important to actually teach these skills to students. The last big idea I want to talk about was data representation. So this one I think is perhaps the least familiar to many statisticians, but what I want to focus on is the idea that most of our analysis methods have been designed with tabular data in mind. So if you think about how you might fit linear regression, well, any linear regression function that you use is really designed with the assumption that your data is already sort of in this tabular format where rows are observations and columns are different variables. But a lot of modern data is not coming in this tabular format. For example, you might have hierarchical data. If you had data on students in schools, well, schools are in school districts, you have multiple teachers within a school, and you might have multiple students studying under a teacher. And so you could store that data in tabular form, but there will be some redundancy, right? Because lots of students have the same teacher, so you'll be storing the same teacher's name multiple times. And so a more natural format for this type of data is XML or JSON. And these formats are things that students really need to know to work with, because a lot of data actually comes in this format. If you get data online, a lot of times it'll be in JSON or XML format, and the students need to be able to work with that. Another common messy data format is raw text. So sometimes students have to, they just have a corpus of text and they have to figure out what to do with that. And that's very challenging. Another example of sort of a non-tabular sort of messy data set is spatial data. With spatial data, we have to store geographic boundaries, and those geographic boundaries are often stored in shapefiles. So what do we do with those shapefiles? I would argue that students need to be able to work with all these different kinds of data. And in particular, what they might be most interested in is how would you wrangle this data from this sort of messy format into a tabular form so that we can take advantage of existing tools. So let me give an example of that. So for example, if you're working with textual data, you might have a corpus of text documents like Dr. Seuss books, for example. And we might want to convert each document to a vector of numbers. And the point of that is to get into sort of tabular form so that we can actually use our tabular techniques. And so one way to convert text to numbers is to have the numbers represent word frequencies. So each number in this table might be for example, the count of how many times a particular word appears in that document. And you might not just want to take the raw word counts, but you might want to normalize or reweight them somehow. And one common scheme that people use is TF-IDF. And this is something you wouldn't get in a statistics class, but you might get from maybe a natural language processing class or a machine learning class. So this is really sort of drawing upon the interdisciplinary aspect of data science. And another thing that people do is we've talked about how do you measure similarity between observations? How do you measure the distance between two observations in your data set? Well, one way to measure similarities between two vectors of word counts turns out to be cosine similarity. Again, that's not a usual similarity or distance metric that we use, but it's an important one that students should know about because people have used this for text processing, and they found this to be more useful than the usual Euclidean distance. So what I would argue is that even though that just the process of working with textual data involves lots of different aspects from different subjects and different courses. So as I said, some of these come from information retrieval, machine learning, natural language processing. But then ultimately, what you might want to do with this data is you might want to fit linear regression to the model to understand how different word frequencies predict some particular response. And so if that's what you want to do, then that actually requires drawing upon ideas from both computer science and statistics. And I think our data science courses should try to be that glue that helps students see all those connections and put it all together. So just to summarize what I've talked about today. So I've argued that our data science courses should be structured around 4 big ideas: manipulating tabular data, framing questions, communicating results, and representing data. And I've argued that these are the important topics because they're actually the ones that are underrepresented elsewhere in the statistics and computer science curricula. Now, if you actually want to be a data scientist in practice, you'll still have to delve into the traditional subjects. You still need to know statistical modeling, you still need to know databases, machine learning, but our data science course, this intro to data science course, should really be the glue that fills in the gaps that makes them a complete data scientist rather than just someone who knows all these different topics. It really helps them put everything together. So thank you all for listening, and I'm happy to take questions at this point.
Well, thank you, Dennis, for that presentation. And if you've got questions for Dennis, please go ahead and type them into the questions box, and we'll ask those to him. We talked about this a little bit before the webinar started, but I'm really curious about how you integrate your work at Google into your teaching.
Yeah, so as Camille mentioned, I actually work part-time as a data scientist at Google. And for me, a lot of these ideas here have been inspired by the work I do at Google. I joined Google straight out of my PhD, and when I joined, I obviously knew a lot of statistics, and I was actually a pretty good programmer. I'd taken a lot of computer science, but I found that there was still a lot of learning I had to do on the job. There are a lot of these ideas that I wasn't actually, for example, like I had not really thought very deeply about the process of manipulating tabular data. I'd never thought about the difference between tidy form and the data cube, and thinking about all these different representations. And so I think that the way I sort of went about designing my data science course and coming up with these 4 topics were sort of what do I think is missing from my statistics and computer science training. And so I thought about what topics would I have needed to sort of to hit the ground running sooner when I started working at Google. So that's sort of how I see my job integrate into my teaching. So it really inspires a lot of the work that I do.
Okay, we've got a few questions. So Anna's asking, first she says thank you, but her question is, what do you do with your students in your first class of your data science course? So day 1, what do you come in with?
That's a good question. So actually, it's interesting. It's actually changed. Every time I've taught this class, it has been completely different. So what I plan to do in this spring is to actually give them this Boston Marathon data set that I showed you, and to just start playing around with it. I'll give them some basic tips on how to use Python, how to read in the data, for example. How do you select columns? How do you select rows? And my plan is just to have them explore questions like, why are Portuguese runners faster than U.S. runners?
Okay. A couple of questions about what background you're expecting students to have, both maybe coming into your intro data science course and what kind of prerequisites you would see for a master's level program.
Yeah, so our data science minor at Cal Poly is targeted at people who have taken 1 course in statistics and 1 course in computer science. So the students are actually coming in with background in programming and background in statistics. So I realize that that's not true for all classes across the country, but I do think that the computational aspect of data science is actually an important part, and it's what distinguishes data science from statistics. It's actually one of the big distinguishing factors, I think, from traditional statistics. And so I think that coming in with this background allows us just to do a lot more and talk about a lot of things. For example, working with the hierarchical data that I talked about at the end, this XML and JSON, that actually requires a fair amount of programming, and so students need some level of comfort with that data. Now, regarding a master's program, I haven't actually thought that much. I mean, Cal Poly, we only teach undergraduates, but I would argue that I think a master's program in data science, depending on the background, especially if the students are coming in from sort of diverse backgrounds, like they may have an undergraduate in biology, some might have an undergraduate in computer science, and so on. I would argue that you would teach a lot of these same topics. I would say that these topics are not ones that are going to be redundant or things that people have seen before. I think it really does take some care and thought to actually cover these topics.
Okay, and I have a couple people asking if they can get a copy of that Boston Marathon data set and where they would go about getting that.
That's a good question. I actually, so I downloaded that straight from the Boston Marathon. I can't remember where I got it from. It was a year ago. It's actually it's available online. It's actually very it's very easy to get. If you just look up Boston Marathon data, you should be able to find the webpage where I got it from.
Okay. A question from Karen says, do you think there should be an ethical use of data component to a data science course?
Yeah, so I think that's a great idea. I haven't figured out a way to work that into the course. I think it needs to be more organic, and I'm not sure that it makes sense to have just like spend a week, say, covering the ethics. I'm not sure that would be the best way to get that idea to sink in. I would want a more organic way of weaving those issues into the course, where they're thinking about ethics in the context of analyzing real data, rather than just like learning a bunch of ethical principles, if that makes sense.
Sure. Question from David says, do you have any thoughts on which academic unit is best positioned to teach the introductory data science course? Is it business, computer science, math, marketing?
So hopefully I've revealed some of my biases in this talk. I actually think statisticians are the best equipped to teach data science because there are a lot of subtle issues regarding inference, regarding variability, regarding causality that are fundamental to data science.
Mm-hmm.
And it's true that I think what traditional statisticians are lacking in terms of their training is sort of more of the computational skills that you need. But I think that those can be picked up. I think at the heart of data science are a lot of statistical concepts that someone in computer science may not be as familiar with. So I think that we as statisticians are well equipped.
Okay, we'll keep it in-house then. And then one last question, and this is maybe broader than you'd want to go into. Lewis is asking, what do you do to keep your students engaged throughout the course? Do you find that they stay engaged just from the data, or is there something specific you do?
So I guess I think it's really important to have interesting data sets. And so one thing I do is I get data sets that are interesting to the students, have interesting issues, and I think that helps students stay engaged. So another data set that I work a lot with is a data set from the TV show Shark Tank. And so that's a show that a lot of students apparently watch. I don't personally watch it, but I think that having data sets that feel relevant to the students is important. I think another important thing to do is to have students work with their own data. And so throughout the course, when I teach a concept, often on my homework assignment on the lab that they have to do for that week that reinforces the concept, a lot of it is sort of take a data set, like for example, if I'm teaching visualization and I'm teaching the grammar of graphics, one of my problems will often be find a data set and produce a visualization. Find your own data set and produce your own visualization, right? Mm-hmm. So I think having them work with a data set that means something to them helps keep them engaged as well.
Okay, and one more. David's asking, are SAS and SPSS still popular as tools for data science, or do you see everybody just jumping on R and Python?
So I think that it really depends on the industry and what you call data science. So I think there's a bias to think of data science as being as synonymous with sort of analytics in tech, specifically in like Silicon Valley tech, the tech industry. And I would say certainly in tech, people do not really use SPSS or SAS. That said, it doesn't mean you can't have data scientists in more traditional companies. And I think in those companies, SAS and SPSS are still alive and well.
Okay.
But yeah, I guess my personal, I also have a little bit of personal bias because working at Google it's a tech company, and so at Google we do everything in R and Python. So
okay. All right, well, thank you so much for your thoughts today, and thank you all for attending. We do have a full slate of additional webinars scheduled in the coming months, as well as ECOTS coming up in May. So I encourage you to keep an eye on your email or on causeweb.org for announcements about those. Thanks again for being here, everyone, and have a great day.